So we do a lot of videos on this channel about futures techniques and foresight methods and so on. So I thought it's about time we looked at some actual trends and possible future technologies that are coming our way. And today we're going to start that series of videos by looking at digital twins. So digital twins are fairly transformative technology that are reshaping industries across the world. And a digital twin is essentially a virtual replica of a physical object, a process, or a system. So you can think of it as a digital mirror that reflects its real-world counterpart. So these replicas are kept up to date using real-time data collected through sensors and IoT devices, ensuring that they accurately represent the current state of their physical counterparts. Digital twins leverage advanced technologies such as AI, of course, and simulation tools. This enables them to model complex behaviors and scenarios that might be difficult or costly to test in the real world. One of their key strengths is to give you the ability to analyze data and make predictions. For instance, they can forecast potential failures or optimize operations before issues arrive. So ultimately, digital twins can help organizations make better decisions by providing insights that improve performance, can reduce costs, and enhance safety. The idea of digital twins was first proposed in 2002 by Dr. Michael Greaves at the University of Michigan. He introduced it as a way to digitally replicate physical systems for better analysis and decision making. The term digital twin itself, however, was popularized by NASA in 2010. They adopted it to describe their use of virtual models for spacecraft monitoring and simulation. The roots of this concept go back even further to the 1960s, when NASA created physical replicas of spacecraft. These replicas were used on Earth to simulate conditions and troubleshoot issues that they might face during space missions. With advancements in technology, particularly Internet of Things, IoT, and AI, digital twins have become much more sophisticated. They now integrate this real-time data and also add predictive analytics to their toolset. Digital twins are widely used across industries, from manufacturing and healthcare to smart cities and aerospace, and are really significantly impacting how we monitor, simulate, and optimize complex systems. So the first step in getting a digital twin to work is real-time data collection. Sensors and IoT devices embedded in physical systems gather this data continuously. So this can include temperature, pressure, motion, or any other relevant parameters based on the use case. Using this data, a virtual model or digital replica of the physical entity is created. This model mirrors the real-world system as accurately as possible, capturing its current state and behavior. The virtual model is then used to simulate different scenarios. For example, engineers can test how a machine might perform under extreme conditions or predict potential failures without risking the actual equipment. Digital twins use these simulations to predict outcomes and provide insights for optimization, so they can suggest ways to improve efficiency, reduce downtime, or even prevent these issues before they occur. So this process operates in a closed feedback loop. Insights generated by the digital twin can directly influence the physical system. For example, if a potential issue is detected, the twin can trigger adjustments in real time to mitigate risks or enhance performance. So DTs, digital twins, are versatile tools that have found applications across a wide range of industries, transforming how many businesses and organizations operate. In manufacturing, DTs are used to optimize production lines, monitor machinery in real time, and predict maintenance needs. For example, companies can simulate production scenarios to improve efficiency and reduce waste, saving costs and resources. In healthcare, DTs are being used for personalized medicine by creating virtual models of human organs and even entire bodies. Doctors can simulate treatments, plan surgeries, and predict patient outcomes with greater accuracy. This can lead to more effective and tailored healthcare solutions. Obviously, with a DT of that complexity, we are many years away from anything close to a perfect replica, but it's a strong start. The aerospace industry uses DTs a lot for predictive maintenance of aircraft, for simulating wear and tear on components under various conditions. Engineers then use this to anticipate failures before they happen, ensuring safety whilst reducing costly downtime. In urban planning, DTs are used to help manage traffic flow, look at energy consumption and optimize infrastructure. So a city can use its DT to simulate the impact of new construction on traffic patterns or test emergency response strategies. In the energy sector, DTs enable grid optimization by monitoring energy distribution in real time. They help improve sustainability by identifying inefficiencies in the energy use and help to most effectively integrate renewable energy sources into the grid. There are three main types of digital twin. Firstly, we can look at asset twins. These are the simplest type. They represent individual components or processes, such as a car engine, a wind turbine blade, or even a human organ. These twins focus on monitoring and optimizing specific assets in isolation. System twins go a step further by modeling interconnected systems. For example, in a factory, a system twin might simulate how various machines interact with one another to optimize production efficiency and reduce downtime. Environment twins are the most complex. They model large-scale networks or environments, such as entire cities or ecosystems. For example, the digital twin of the city we mentioned earlier that looks at traffic patterns, energy consumption, infrastructure management, and generally the best ways to improve urban planning. The key difference between these types of digital twin lies in their scale and complexity. Asset twins focus on small-scale details, while system and environment twins deal with large and intricate interactions between multiple smaller systems. These types of digital twins, industrial twins, are applied across industries. Asset twins are common in manufacturing and healthcare, system twins in aerospace and energy, and environment twins in smart cities and climate modelling. So digital twins rely on robust technologies to function effectively. They have to work together for this real-time data collection and produce analysis and actionable insights. The Internet of Things forms the backbone of digital twins by enabling real-time data collection. Sensors and connected devices gather information from the real world and then feed it into the digital model. AI and machine learning are critical for advanced analytics and predictions. They process these often massive data sets to identify patterns, simulate scenarios, and forecast potential outcomes. Digital twins demand significant computational power to process vast amounts of data. Cloud computing is key to providing scalable resources for heavy data processing, while edge computing, this allows you to process data closer to the source, reducing latency for time-sensitive applications. Blockchain is being integrated into digital twin work by creating tamper-proof records of transactions and changes. So this can be particularly important in sensitive applications like healthcare or critical infrastructure. High-speed networks, 5G networks, enable fast and reliable communication between physical assets and their digital twins. So with low latency and high bandwidth, 5G supports real-time updates and seamless integration across systems. Benefits of digital twins we've really touched on already. They provide real-time insights by analysing data from physical systems, allowing businesses to make more informed decisions, whether it's optimization or managing complex systems. The ability to simulate scenarios also helps in planning for future challenges. One of the standout benefits of digital twins is predictive maintenance. So by monitoring equipment in real time, digital twins can identify potential issues before they escalate into failures. This reduces downtime, reduces maintenance costs, and ensures smoother operations. Digital twins help optimize resource use, improving efficiency whilst reducing waste, for example, in energy grids or manufacturing plants. They can identify inefficiencies and suggest improvements, which helps these companies commit to their sustainability goals by lowering emissions and conserving resources. By using digital twins to test and validate designs virtually, companies can accelerate innovation cycles. So this eliminates the need for physical prototypes, often many physical prototypes, saving time and costs while bringing products to the market faster. And digital twins enhance product reliability by enabling continuous monitoring and refinement based on real-world performance data. This iteration can lead to more reliable products that meet customer needs more effectively. So digital twins obviously offer immense potential, but their use doesn't come without some challenges. One of the main ones being a seamless integration and interoperability between various systems, devices, and platforms. Digital twins often rely on data from diverse sources such as Internet of Things sensors, software systems, and other technologies. Without standard protocols or compatibility, these systems can struggle to communicate effectively. Digital twins are only as good as the data they receive, so poor data quality or inaccuracies can lead to flawed simulations, incorrect predictions, and suboptimal decisions. Ensuring there's a feed of clean, reliable, and consistent data requires robust data governance and validation processes. Given the sensitive nature of the data handled by digital twins, especially in healthcare or critical infrastructure, cybersecurity risks are a major concern. Unauthorized access or data breaches could compromise not only the digital model, but also its physical counterpart. And privacy concerns also arise when personal or sensitive data is involved. Digital twins require substantial computational resources to process this data, to run simulations and generate insights. This can strain existing IT infrastructure, requiring a company to make significant investments in cloud computing, edge computing, or even emerging technologies like quantum computing. And as digital twins become more autonomous and interconnected, there is a pressing need for clear regulatory frameworks. So these frameworks must address issues like who is liable in the event of an error and ethical considerations in the decision-making algorithms. So digital twins are evolving rapidly, and there is great potential for their future use. One of the most exciting advancements is what we've just mentioned, which is autonomous decision making. So future digital twins may not only simulate and predict outcomes, but also act independently to optimize systems, such as automatically adjusting energy grids or responding to emergencies in smart cities. As quantum computing matures, it will provide the computational power needed to handle the vast complexity of interconnected digital twins. So this should enable the simulation of highly intricate systems such as climate models or global supply chains with unprecedented speed and accuracy. Digital twins are expected to become more interconnected and interoperable. For example, city-wide digital twins could integrate with industrial or healthcare twins to create comprehensive ecosystems that share data and insights for improved decision-making across multiple sectors. Future applications will expand significantly. In healthcare, human digital twins could revolutionize personalized medicine, enabling precise simulations for treatments or surgeries. And in urban planning, city digital twins could optimize resource allocation, reduce emissions, and just generally enhance quality of life for residents. So one final note on ethical and security considerations. DTs rely on vast amounts of sensitive data, including personal, industrial, and even national security information, and this can create significant privacy risks if the data is mishandled or accessed without authorization. For example, human digital twins could expose personal health data, while city twins might reveal vulnerabilities in public infrastructure. Digital twins often use AI and machine learning algorithms to simulate and predict outcomes, and the quality of these outcomes depends on the quality of the algorithms, and the quality of the algorithm depends on the quality of the data that was used to train it. So clean, reliable data used for training is an absolute must for a fair outcome. The interconnected nature of digital twins makes them vulnerable to cyber attacks. Hackers could manipulate a twin's data or operations, potentially causing real-world harm. And as digital twins evolve towards autonomy, questions arise about accountability. So who is responsible if a twin makes a harmful decision? If a digital twin of a city makes errors in managing traffic signals, for example, and this leads to car accidents and injuries, who is liable? Is it the supplier of the digital twin? Is it a team? Is it a government organisation at a local level or a state, national level, and so on? And there is, as we touched on, a need for clearer regulatory frameworks that can address the complexities of digital twins. So DTs like AI, machine learning, and a lot of technologies that are rapidly evolving are moving far, far quicker than the legal frameworks that we have in place. So laws only get updated every so many years, often many years in between each update. Meanwhile, in the space of 2 or 3 years, the field of AI or digital twins could have completely shifted and radically transformed. So that's our quick look at digital twins today. I hope you found that interesting. It is the first of a series of videos about future trends. If it's something that you're interested in, hit the subscribe button. There are plenty more videos coming, and I look forward to seeing you in one of those. Bye for now.